So previously we talked about QDA, quadratic discriminant analysis, where the discriminant function on which we're going to make this classification decision takes this form. The first term is a quadratic function involving the mean of each normal, mu k, and also the inverse of the covariance matrix for the kth group, and plus some other terms involving the mixing weight, pi k, and also the covariance matrix sigma k. If we further assume all the groups share the same covariance matrix, sigma k is equal to a common sigma, like this, then the discriminant function we need to compute will take this form. The first term, again, is a quadratic function, measure how far the data point x is from the case center mu k in terms of the Mahalanobis distance, and then the determinant of sigma and minus 2 log of pi k. Here I color the log sigma in gray color, meaning that we actually don't need to evaluate this, because when we are evaluating those discriminant function d sub kx, the purpose is to try to pick the k value that minimizes this dk for every x. But because log sigma is the same for every k, so we really don't need to evaluate this term anymore. And we can even further simplify the first term. It looks like a quadratic function of x, but if you expand this quadratic term, so you have the x transpose sigma inverse x transpose sigma inverse mu, and plus another term involving mu k. And then you realize the first term, which is in gray, it is a common term for all the k, so we don't need to evaluate this term. And the remaining function is actually a linear function of x. So this is why when we assume all the covariance matrices are same for all the Gaussian distribution for all the classes, then we are back to linear discriminant analysis, because the discriminant function is a linear function, and when we are looking at the decision boundary, for example, when k is can only take two different values, when we evaluate the locations of x where the dk1 is equal to like d1x is equal to d2x or d0x, and those, because each of them is a linear function, so the points x, which determine the decision boundary of this binary classification problem, is actually going to be a linear function of x. So this is why we have the name LDA. In practice, how we can estimate our pi k, mu k, similarly as what we did for the QDA. How we estimate sigma, the shared covariance matrix, that's often estimated by this pooled sample covariance estimation. Pooled means we pool the information about covariance from the capital K different classes. For every xi, we subtract its own cluster mean or group mean, mu sub k, and then this is going to be a column vector, this is a row vector. So sum together is a matrix, P by P, and we sum over this over all the over k groups and every observation each of the group, and then we average by 1 over n minus k. So that's our estimate for sigma. In the discriminant function, what's relevant is sigma k inverse. So what if sigma k is not invertible? The rank of sigma is at most n minus k. For example, let's consider the digit example. You can find the data from the R code page. This is an example used in a lot of machine learning and data mining courses, where we have an image 16 by 16, meaning our feature vector is a vector in a 256 dimension, and the label y is just what is digit shown in this picture. So it could be 0, 1, all the way to 9. So this is a multi-class classification problem where k is equal to 10. So suppose we have 200, our training sample is 200, So we have 200 samples, and you're going to find out this sigma is definitely not a full rank, because sigma is going to be a 256 by 256 matrix, but its rank is at the most 290. So if we cannot take inverse of this estimated covariance matrix, we can easily solve it by using the trick we used for QDA, which is an old ridge regression trick, meaning we're going to just add a eta times an identity matrix, then we can take inverse. Or we can compute the so-called generalized inverse of this matrix. What is a generalized inverse? Let's assume the dimension P is 3, and hypothetically assume that we are dealing with a case where the real rank of sigma hat is not 3 but 2. That means the sigma hat, the covariance matrix, admits the following singular value decomposition form. So U times a diagonal matrix times U transpose. Here U is often called the rotation matrix or orthonormal matrix. So U is going to be a 3 by 3 matrix, and every column is of norm 1, and they're orthogonal to each other. So U transpose should equal to identity. Now, for this, the rank of sigma is 2 means that in that diagonal matrix in the middle, we only have 2 non-zero entries, which are all positive. D1, D2 are positive, but the third one is 0. So we cannot take inverse because we need to deal with something like 1 over 0. But what is the generalized inverse? The generalized inverse just ignore the last dimension. You just take inverse of this diagonal matrix for the first 2 dimensions. Just leave the last 0 as 0. The rationale is that the third dimension is sort of the null space of this covariance matrix. It basically means if I use my U as new coordinates, then in the third dimension, none of the data actually sit in the third dimension, so we can just ignore it. This is why when we take inverse, just ignore the third dimension and only do the inverse for the first 2 dimensions. We can use this is called generalized inverse. We can use this trick for LDA, but we cannot use the trick for QDA. The reason is in QDA, we have to deal with different covariance matrices. And the null space for those capital K different covariance matrices may not be the same. So we cannot just ignore one dimension only for one group and ignore other dimension for other group. So that won't work. But for LDA, because they have the same covariance matrix, so so that null space is sort of shared by data from all the groups, then we can just ignore that.